So I'll introduce our final keynote speaker, Christian Posta.
We made it. The last talk of the day. Thank you all for coming out. Thank you, huge round of applause even for the organizers of this conference. It's not easy to put a conference on like this, and this has been a wonderful conference, so thank you guys for having me. I'm painfully aware that I'm between myself and beer, so let's get into this as quickly as we can. The last buzzword that we'll talk about today is Service Mesh. How many people have heard of Service Mesh? Okay, all right. Marketing engines are spinning up, that's good. My name is Christian. I'm a chief architect at Red Hat. I spend my time working with our customers across mostly North America to help build distributed systems on cloud platforms, namely Kubernetes, and at Red Hat, our distribution of Kubernetes is OpenShift. But I've spent a lot of time in open source. I started my open source career building or helping to build messaging systems. So if you're familiar with Apache ActiveMQ, anyone? I've contributed a little bit to Apache Kafka and a few more projects. And more recently, or I guess now it's been a year and a half, I've been contributing to a project called Istio, and we will be talking about that. I've written a few books. The latest one I'm working on is called Istio in Action, so go buy it. It will be a in-depth treatment of Istio, how it works, why you might use it, when not to use it, which might be even more important, and it's in early access right now. So if you do go buy it, you will be getting only the first 3 chapters. The rest of the chapters are forthcoming, and I'm going to have to finish it if you actually do buy it. How many people are doing microservices or something that sounds or feels like microservices today in your organizations? Good. So microservices, everyone has their own definition for what microservices is. Mine is well, kind of you can't read it too well with that line through it, but it is an optimization of your application architecture to go faster when your application architecture has become a bottleneck, right? This is not, so I guess I can go into a lot more detail about this, because there's times when you do go toward a microservices architecture, and there's definitely times when you do not. It is an optimization, which means you do take on complexity to get there. So make sure that you're getting the benefits out of it. But when we go to a services-style architecture like that, where we're deliberately breaking components of our application into smaller pieces that then communicate over the network, we're introducing a lot of opportunities for things to go wrong. In our traditional ways of building monolithic or co-located style applications, we have the comfort of assumptions that were baked into the programming model. When we make calls to other components, they would succeed. Or when we wrote to databases, we could take advantage of atomicity and isolation, concurrency isolation in the database. Once we start to break things down for the purposes of going faster, we're going to see that these services need to interact with each other for them to accomplish any kind of business process or business value, right? But again, the point of microservices is to optimize your architecture to go faster for when your application architecture has become a bottleneck itself. Now, how many of you follow the survey results from the DevOps report, State of the DevOps report? If you could raise your hand. It's a DevOps conference, I would hope some of you, okay. This is from the 2017 report. Yeah, 2017 report. We can see that, and I've seen this with our customers, that the rate of change, how fast you can actually go, measured in deployment frequency, so the number of times you're able to do deployments, or how quickly you can get code committed to your source code repository into production, the rate of change between high-performing teams and low-performing teams is shrinking. In 2016, we see that delta about 200 times for deployment, number of deployments, and 2,500 times faster from get commit into production. And in 2017, we see that number shrinking, right? In some ways, this can be attributed to, well, okay, we're taking that message to heart, that service architectures, that automation, that containers, all this stuff helps us go faster, that it helps us deploy faster and get things out there. But the problem with that is we can't just deploy code into production willy-nilly if it's having adverse effects, if it's creating instability in our system. The last two metrics that the DevOps report uses to measure high-performing teams, mean time to recovery and the number of failures that you introduce into your system for the number of deployments, that window is growing. We're introducing more failures. We're going faster, but we're producing crap, right? So that is not ideal, but how hard can this really be, right? We've eschewed the ESB. We said we're going to just do APIs and microservices, right? We're just going to interact directly with each other. How hard can that really be? Now, I'm not going to hammer this too far. You probably have seen the fallacies of distributed computing. You probably, we've been kind of talking about that because A doesn't really talk to B, right? A talks to B through this unknown, unpredictable mangle of network that requests, that packets have to hop through, asynchronous networks, where there's no notion of A and B don't agree on time, and you put a packet on the network and it might get there within a reasonable amount of time, it might not. It might get duplicated, it might get lost, the network might sever itself, it might get to the other side, and the other side is slow, or the other side starts to fail. And from A's point of view, we have no idea whether that's the network or the other side, whether that's application B, so we might try again, and so now you have to deal with duplicates, either injected by the network or by the application, so you get this kind of chaos and this kind of complexity. As we move to these services architectures, we have to deal with this complexity. This is inherent in going this route. What are some of the concerns that we have to solve for when we start to go toward distributed applications and even moreover, distributed applications running on cloud infrastructure? Cloud infrastructure whose premise, including Kubernetes, whose premise is when you deploy an application, those containers, those VMs, if you deploy into a public cloud on VMs, those are fungible things. Those could just die. Those could go away. How do we build our applications knowing that the infrastructure that we run on, the compute, the networking, the storage, all that stuff could fail and probably will? We have to solve for things like topology changes in our application, services going away randomly, services being spun up, auto-scaled, or rebalanced, or moved. So service discovery, load balancing, these types of things, our applications need to be able to deal with that. Resiliency aspects, when services start to misbehave, and they will. Circuit breaking and timeouts and retries. Right? So our applications, somehow, this needs to be solved. We can't ignore these things. With the power of these cloud platforms, we have the opportunity to lower the risk of doing deployments by controlling traffic, shaping traffic, controlling requests. So we can do things like routing, adaptive routing, surgical routing, canary-type deployments, canary routing, traffic shaping, and request shadowing. These types of things are opportunities for us. We can implement A/B testing on top of that, fault injection, possibly. We had the opening keynote about chaos testing and so on. So these lest I forget, you can't make changes to your system and go quickly if you don't understand what it's doing, what it's doing now in a steady state, in its ideal state. What is it doing? How do we collect information about that? How do we observe how it's behaving? And then when we make changes to it, did we actually get the outcome we were expecting? We need to collect telemetry. We need to collect distributed tracing and logs and all these stuff and marry them together. The last thing, as we start to move toward distributed computing to more ephemeral and elastic infrastructure, and even potentially infrastructure that we don't own, that we lease from our cloud vendor, we have to put security first and foremost in how we build these applications. Now, the big cloud vendors, so the Googles, the Amazons, and so on, they've known about this stuff for a while. I spent some time at Zappos.com and worked very closely with the Amazon teams back in 2013. This was all kind of, they already knew all this stuff. Netflix, when they started talking about their open source, or their implementation of a services architecture, and they started to open source some of the libraries and projects that they used to build that up, which was very nice of them. A lot of the big internet companies didn't open source at that time their internal learnings. They built up a set of libraries, a set of frameworks to solve some of these problems. How many of you are familiar with the Netflix OSS libraries from a Java perspective, really, because that's how it started off, handful. So these libraries were built to be embedded in your application, in your JVM or Java-based application, to handle things like circuit breaking and timeouts and retries and client-side load balancing and service discovery and distributed tracing and so on, right? So when you, as an application developer, started to adopt these things, you would have to bring that into your application, figure out exactly how to use the right libraries and right commands to facilitate this. And then if you decided you were going to use a different Java framework, like Spring had a derivative called Spring Cloud Netflix that implemented some of this stuff, made it a little bit easier. But if you used a different JVM framework, like maybe Vertex, you would have to go figure out, all right, well, how do I solve those same problems the Vertex way, right? So you go Google and you figure out, okay, well, there's a couple of those implementations exist. Well, what if you don't want to use Java? What if you want to use Node.js? Then you go on, Google again, all right, well, history.js, and I think there's this thing for distributed tracing, and then other people want to use Go, and other people want to use Python. How many people Python? Python? Yeah, awesome. And believe it or not, Perl still exists. Perl still exists. So for each one of these libraries, each one of these frameworks, each one of these different languages, we have to solve that long list of problems that I showed. And to do that in the past, otherwise we would have to go and just figure it out, build it ourselves, or figure out what libraries somebody else built and open sourced maybe, and hope, cross fingers, and really hope that each one of those implementations were built exactly the same and behaved exactly the same, right? So obviously there's some drawbacks to that. If you start to go the library approach, you either have to lock down the number of languages that you use, or you end up with this proliferation, combinations of different libraries and partially complete implementations of these different concerns that we have to solve for. And you had to maintain it. Anytime you made a change to one library, you'd have to implement the same change in the other ones. Those libraries were pretty invasive in the application. It would bring along dependencies, transitive dependencies, so on, get pretty co-tangled into the code and so on. And so those were pretty intrusive implementations for solving some of these problems. What if we could step back and take the container way of thinking about this? And what I mean by that is, let's abstract away having to know the details of these different languages and these different frameworks, the same way we kind of abstracted away deployment, right? We don't, now with containers and Kubernetes, we don't really care what's in the container. From a different perspective, we should, but from the deployment perspective, starting and stopping the container, doesn't matter if it's Java or Node.js or Golang. Auto-scaling the container, health checking, we do that exactly the same, regardless of. So what if we took that same approach for problems that were very horizontal problems, that were not language specific and they're not business differentiating problems, and treat that the same way with these problems. So if we could consistently apply circuit breaking, timeouts, retries, service discovery, load balancing, rate limiting, this type of stuff to our applications, and implement it consistently in one spot and let any application take advantage of it, that would be a little bit cleaner and less burden on operations and operating your services going forward. So if we start to think about what that might look like, using a proxy is kind of the pattern that's emerged in the communities today. And this proxy is built specifically to live with a service instance, to implement these types of things, timeouts, retries, circuit breakers, and so on. As we start to deploy this out in our cluster and deploy these service proxies alongside each one of the instances of our application, we start to form a mesh. The applications are communicating with each other through their individual proxies, which basically act as interceptors and enrich the network traffic with these types of behaviors that we need to implement one way or the other. And that's where the definition of service mesh comes from. It is decentralized application networking infrastructure that lives between the services, that is application aware, that can help implement things like resiliency, observability, security, traffic control, and policy enforcement. And we're going to take a look at what some of those implementations look like. So the general pattern or general architecture for what the service mesh looks like is you have your applications and your application instances co-deployed with a service proxy. That proxy lives with each instance. So think your Tomcat instance has a proxy co-located with it. Your Node.js instance has a proxy co-located with it. Now those proxies need to be managed, they need to be configured, and we need an API to do that. So that's where the, see if this fancy thing works here. No? No? There. That's where the control plane comes in. Control plane allows, gives an API for operators of the infrastructure of your services to be able to manipulate the proxies to do and behave the way we're expecting for those different parameters, like service discovery, load balancing, and so on. The bottom part here, where the requests are actually flowing through the system, through the mesh, we term that the data plane. The requests and messages, the data that the applications are exchanging, flow through the proxies. That's the data plane. The API, the control layer, is the control plane. So let's walk through very simplistically what kind of how this works. So when an app is deployed, it gets deployed with its proxy. Now you can think of the unit of deployment. Well, if you think about it in terms of Kubernetes, it's pretty straightforward, right? Because Kubernetes has pods, which are atomic deployments of multiple containers. And in this case, your app would be a container, and the proxy would be a container. But this could be a VM, where you have your app co-deployed with the proxy running on that VM. When the app wants to talk to an external service, like one of its collaborator services, or a database, or a cache, or a queue, or whatever, it wants to talk out over the network, it talks through the proxy. The traffic goes from the app through the proxy. Now, in some implementations of Service Mesh, the proxy is actually transparent. The app doesn't even know that it's there, and we can talk about that in a sec. But so the traffic goes through. When it gets to that proxy is in charge of doing client-side load balancing. So if it wants to talk to service B, it'll pick which endpoints of B are least loaded, so it can do some complex load balancing. It will do service discovery, so when it wants to talk to B, it knows, the proxy knows where B lives, and if B is auto-scaling or failing or whatever, those endpoints, it keeps track of that, not the application itself. The proxy can do things like circuit breaking, request timeouts, request retries, and this type of stuff. As the request goes out over the network, the proxy can do interesting things transparently to the application, like encrypting the traffic, upgrading that TCP connection to neutral TLS in this case. So when we talk to the other application, it's actually going to a proxy where we can configure both proxies to say, hey, encrypt this using mutual TLS. Now, once it gets onto the other side, the proxy on the other side can be in charge of enforcement. Is app A even allowed to talk to app B? We'll decline that traffic if not. Right, so we can set up policies about which workloads are allowed to interact with which and enforce that through the proxies. And then all the while, all this is happening, requests are flowing through the system, requests might be failing. We are, oh, that is washed out. We are keeping track of metrics and telemetry. The proxy is keeping track of number of requests, latency, all that stuff, and sending that back to the control plane, sending it back to things like Prometheus or Datadog or whatever backends you really want to use to collect this type of stuff. It's also doing things like distributed tracing. So it can manage sending distributed tracing spans to your tracing backends like Jaeger or Zipkin or whatever. So the control plane will manage all those backend, configuring the proxies, setting up the telemetry syncs and distributed tracing syncs, and writing policy about what services are allowed to interact with which. So at a high level, Service Mesh typically implements this type of functionality. Stuff that I've kind of just walked through. Let's look at 3 different open source projects that implement the Service Mesh pattern. The first one is called LinkerD. How many people have heard of LinkerD, if you could raise your hand? LinkerD is part of the CNCF. It started off as a Java-based or Scala-based, JVM-based implementation. It basically took Twitter Finagle and put it in a container and said, all right, well, let's just route all the traffic through this. Now, that worked out to some extent, but it also had some drawbacks. Because if your service is a Node.js service that takes, I don't know, 50 megabytes of RAM to run, and you run a JVM next to it to implement all this stuff, which probably takes 256 megabytes just to start up, that's not going to work out too well. Now, the LinkerD folks at Buoyant, a startup called Buoyant, implemented a thing called LinkerD 2, which just recently went GA. LinkerD 2 is based on a model where the proxies are actually built in a language called Rust, and the control plane is built with Golang. And is very focused, what I like about LinkerD is very focused on developer experience. Much in the way Docker was very focused on developer experience and getting started, LinkerD has done a good job of implementing the developer experience. They've kept the scope of the functionality kind of small and focused. We're going to do mutual TLS. We're going to do some resilient stuff and observability stuff, right? And so their architecture matches what a typical Service Mesh implementation would look like, where the proxies run co-located with the applications, and the control plane exposes a web UI, allows you to manage the Service Mesh, and allows you to set up things like Grafana and Prometheus to capture metrics. The second project I'll talk about is called Consul. How many people currently use Consul? Anybody use Consul? Awesome. Consul kind of started off as a service discovery registry, where you can store information about your services and their endpoints and their whereabouts, and discover at runtime how to find them. They've since built onto that, called Consul Connect, that allows, when services interact with each other and connect with each other, allows the services to establish things like mutual TLS and policy about which services are allowed to interact with which. Consul Connect came out in, I think, June. Is that what I wrote? June. And in Consul 1.2, 1.3 is the latest, 1.4 is about to land, and these features are continuing to harden and become more stable. Now, Consul Connect uses a model where the individual hosts where the workloads are running actually have a Consul agent. Well, if you're familiar with Consul, then you're familiar with this pattern probably. But the Consul agent is in charge of bringing up the proxies for each of the application instances and configuring those proxies. And for a while, when it first launched 1.2, the proxy was a homegrown little proxy. Right now, they're leveraging a project called Envoy proxy. How many people have heard of Envoy? Awesome. Another CNCF project. The last project is Istio. Istio is an open source project that was started by Google, IBM, and Lyft, and is now expanded to include lots of different contributors, including at Red Hat. We are going to bring Istio into our open source or OpenShift product. It went GA 1.0 at the end of July, but as much as I like Istio, and I'm writing about Istio, I will caution you, 1.0 does not necessarily mean throw it into production right now. I would say Istio is at a level where you absolutely should be, if you're doing this on-prem, you absolutely should be looking at it and kicking the tires and understanding how it's going to fit into the rest of your architecture. But give it a couple more releases before you put it into production. That's my guidance. Istio implements all of those service mesh capabilities, is pretty ambitious insofar that it is not trying to be any type of platform specific. It wants to run on, it's built to run on Kubernetes right now, but that was just the first platform. The abstractions are in place to run Istio on VMs, on Cloud Foundry, on Mesosphere, on any deployment platform. That's the idea with Istio, to be able to connect workloads regardless of whether they're running on a particular deployment platform, whether they're running on-prem or in public cloud. Istio follows that similar pattern, architecture pattern for Service Mesh, where we have the control plane, in this case off to the left, where we have a component for doing the configuration, a component for injecting and managing the certificates, to be able to do the mutual TLS that I mentioned earlier, and a component to handle aggregating and syndicating back the telemetry that gets collected from the data plane. Istio also uses Envoy proxy as its service proxy, so when Istio injects the service proxy into your applications, into your workloads deployed onto Kubernetes, it's actually Envoy. Now, I think, have 6 minutes or 5 minutes. Let me see if I can do a quick demo and see if that will cooperate for me. Reach out to me anytime if you have any questions about this talk. Check out these links. I also want to point out, like I did earlier, that I've been involved in open source for a little while now, and I'd like to extend an offer to help people who are interested in contributing to open source navigate the sometimes seemingly insurmountable path to get there. So if you just reach out to me, I'll be happy to kind of mentor and give you some things to watch out for when contributing to open source. All right, let's get to the demo. Is going to look like this. We're going to do a fairly simple demo of service resilience. The architecture for the demo will look like this. A customer service will be at the edge. We'll interact with the customer service. That service will call preference, which will then call the recommendation service. We'll do some interesting things between the communication of preference service and recommendation, like introduce failures or introduce a new version and so on. So let's take a look at that. Luckily, I planned ahead enough, I think, to run this live demo without actually having to type too much. This is a live demo. It could absolutely crash, and it has many times, but cross your fingers for me here. Okay, so if we look at our Kubernetes cluster, if you guys can see that, I can make it a little bit bigger. Is that all right? Can you guys see that in the back? All right. We have our customer service, we have our preference service, and we have our recommendation service. We have Keycloak in there also, which is an open source SSO project. That's for a security part of the demo, but we're not going to be able to get to that. So the first thing we're going to do is, on the bottom, cross our fingers. All right. On the bottom pane, we have a script, a loop, that just calls the customer service every second. Right? We can see customer call, preference call, recommendation v1. Let's say we want to deploy a change to our recommendation service. One thing we don't want to do is just deploy it out there and take the old one out. right? Because if we deploy something out there that introduces issues or failures to our customers, they're going to see it right away and they're going to complain. And even if we were able to roll back to version 1, that's not actually the version 1 that was running before, right? So what we want to do is control the rollout of that release. So what we're going to do is take a look at our deployment. This is a regular Kubernetes vanilla deployment of the recommendation service. We can see our container image right here. What we're going to do is we're going to manually inject the Istio sidecar. Now, you can set up Istio to automatically do the injection, so you don't have to deal with this, but I'm doing it for illustration purposes. We're going to inject the sidecar. Here we can see init containers and extra containers for the proxy. And eventually, if I keep going up, you should see some config and the actual application image right here, as we saw in the previous resource file. So it's just the resource file enriched with a couple of extra, well, one extra container and one extra init container with some config. So let's deploy this. We'll apply the output of that kube inject, that Istio sidecar injection, and we will watch it. You can start to see some activity here at the bottom, 503s. Don't worry about that. I'll come back and explain that. And we can see that recommendation v2 is running. And on the bottom, the traffic is actually being split across v1 and v2. We do not want that. We do not want to just deploy stuff into production and immediately show it to all of our customers. We want to be able to control how that unfolds. So to do that, what we're going to do is, using Istio, we're going to create a rule, which is basically another YAML file. Istio uses CRDs in Kubernetes, so if you're familiar with that, you can use kubectl to create the rules here. And this rule basically just says, route everything, if you're talking to the recommendation service, route everything to v1 of the recommendation service. So as we can see, we created that rule. Now all the traffic at runtime is going to only v1. Now we're going to use Istio to, on purpose, balance the traffic between v1 and v2. Right now it's set up for 50-50 because other parts of the demo show better if it's 50-50, but I could have done 1% and 99. Right? We could have said, let's just take 1% of the live traffic and funnel that off to our new deployment, and look at our telemetry, look at our logs, look at our distributed tracing, and look at everything and observe how it's actually behaving in production. We could have done something else that Istio can do, which is called traffic shadowing, which instead of taking a 1% or a percentage of live traffic, we could make copies of the traffic and send that to our new deployment. So we're taking live production traffic, siphoning it off to the new deployment, but we're not impacting any customers, even if things do go wrong. Right? So we can take shadow traffic. There's other parts of this demo, and if you go onto here, you'll be able to actually, it'll walk you through step by step through all of these pieces and how that works. I am out of time. It is now time for beer. I'll be here for another hour or so I'll be happy to take questions in the hallway track. And I appreciate, again, thank you guys and gals for coming out. It's been a great conference.